In the first part of chapter 5, we have mainly been dealing with norms on vector spaces. The second part of chapter 5, which is this video, will be looking at inner products. We begin this part by definition 5.12 of an inner product. And it reads as follows. Let V be a vector space. An inner product on V is a function that maps two vectors from V into the field such that for all vectors x, y, y1, y2, and all scalars alpha, we have the following three properties. First, conjugate symmetry, which means that whenever we take an inner product of a vector x with another vector y, then this equals to the complex conjugate number of the inner product of the vector y with the vector x. Second, we must have linearity in the second argument, which means the usual two conditions, namely the inner product of x with alpha times a vector y must be the same as alpha times the inner product of x with y, and also the inner product of x with the sum of two vectors y1 plus y2 must be the same as the sum of the inner products of x with y1 and x with y2. Third, we must have the property of positive definiteness, which means that if I take the inner product of a vector x with itself, then this must always be non-negative, and moreover, the inner product of x with x can be zero only if the vector x itself is the zero vector. We will call a vector space together with an inner product defined on the vector space an inner product space. From definition 5.12, we have an immediate consequence that's stated in fact 5.13, namely an inner product satisfies a conjugate linearity property in the first argument. This means that if we take a scalar multiple of the vector x in the first argument of the inner product and take the inner product with another vector y, this is the same as taking the complex conjugate of the scalar alpha and multiplying it with the inner product of x with y. And also, if we take a sum of two vectors, x1 and x2 in the first argument, and take the inner product with a vector y, this is the same as the sum of the inner products of x1 with y and x2 with y. Let's quickly look at the proof of fact 5.13. It's fairly simple, but it will help us to familiarize ourselves a little bit with the definition of an inner product. For the first part, we start with the inner product of the vector alpha x with the vector y, and by the property of conjugate symmetry, we can write this as the complex conjugate of the inner product of the vector y with the vector alpha x. Next, we can use linearity in the second argument to pull out the scalar alpha in front of the inner product, and the complex conjugate of this entire expression is of course the same as the complex conjugate of alpha times the complex conjugate of the inner product. And now we use again the property of conjugate symmetry for the inner product to obtain that this is equal to alpha bar times the inner product of x with y. The proof of part 2 works in a similar manner. We start with the inner product of the sum of the vectors x1 and x2 with the vector y. By conjugate symmetry, this is the same as the complex conjugate of the inner product of y with the sum x1 plus x2. By using linearity in the second argument, this is the same as the complex conjugate of the sum of the inner products of y with x1 and y with x2. And by the rules of complex calculations, this is of course the same as the sum of the complex conjugate of the inner product of y with x1 and the complex conjugate of the inner product of y with x2. And now we can use conjugate symmetry on both of the terms again to show that this is equal to the inner product of x1 with y plus the inner product of x2 with y. Here are some examples of inner products and inner product spaces. The first one is Rn with the usual inner product of two vectors x and y defined as x transpose y. Analogously, of course, the space Cn with the inner product of two vectors x and y defined as x star y. Then the sequence space little l2 with the inner product of two sequences x and y defined as the sum over all elements k equal 1 to infinity of the complex conjugate of the kth element of x multiplied with the kth element of y. Also, the function space L2 of square integrable functions on the interval AB is an inner product space with the inner product of two functions f and g defined as the integral from a to b of the complex conjugate of the function f multiplied with the function g dt. For any inner product space, we have a very fundamental result that's known as the Cauchy-Schwarz inequality, and it's stated in Theorem 5.14. So let V be an inner product space, then for any two vectors x and y in V, we have the following inequality. The absolute value of the inner product of x with y is always less than or equal to the square root of the inner product of the vector x with itself times the square root of the inner product of the vector y with itself. Now to the proof of Theorem 5.14. It is easily checked that the theorem holds if we choose the vector y to be the zero vector. We may hence assume that the vector y is non-zero by the property of positive definiteness of an inner product. For any scalar alpha, we have that the inner product of the vector x plus alpha y with itself must be greater than or equal to 0. And by linearity in the second argument, this can be written as the inner product of x plus alpha y with x plus alpha times the inner product of x plus alpha y with y, which by conjugate linearity in the first argument can be written as inner product of x with x plus alpha bar times the inner product of y with x plus alpha times the inner product of x with y plus alpha bar times the inner product of y with y. Remember that this works for any scalar alpha in the field F. So we may pick a particular alpha, which is defined here as minus the inner product of y with x divided by the inner product of y with y, where the denominator is non-zero because we have assumed that the vector y is non-zero. Note that by conjugate symmetry, alpha bar is equal to minus the inner product of x with y divided by the inner product of y with y. So substituting alpha and alpha bar into the above condition yields the following inequality. We notice that in the last term, the inner product of y with y cancels out, and then the third and the fourth term are the same but with opposite signs. So also these two terms cancel out. Now we bring the second term to the other side and we get this inequality that we can now multiply with the inner product of y with itself, and we get to something that already looks very similar to the Cauchy-Schwarz inequality. Now the Cauchy-Schwarz inequality follows with the conjugate symmetry of the inner product of y with x, which is equal to the complex conjugate of the inner product of x with y, and a complex number multiplied with its complex conjugate equals to its absolute value squared. And now all we need to do is take the square root on both sides of the inequality. As a direct consequence of the Cauchy-Schwarz inequality, we have corollary 515. It states that if V is an inner product space, then the square root of the inner product of a vector with itself can be used to define a norm. And this norm is called the induced norm of the inner product. For the proof of corollary 515, we simply have to verify all three properties of a norm as stated in definition 5.1. The first one is positive definiteness, which is clear from the positive definiteness property of the inner product. The second one is absolute homogeneity. To show this one, pick any vector x in the vector space and any scalar alpha in the field. By definition of the induced norm, the norm of alpha x squared equals to the inner product of alpha x with alpha x. Now we use conjugate linearity in the first argument to pull out the first scalar, and linearity in the second argument to pull out the second scalar. And what we get is alpha bar times alpha times the inner product of x with itself. And since alpha times alpha bar equals to the absolute value of alpha squared, and the inner product of x with itself equals to the induced norm of x squared, the absolute homogeneity property follows by just taking the square root on both sides of the equality. Finally, for the proof of the triangle inequality, pick any two vectors x1 and x2 in the vector space, and notice that by the definition of the induced norm, the norm of x1 plus x2 squared equals to the inner product of the vector x1 plus x2 with itself. This expression can now be extended by using linearity in the second argument and conjugate linearity in the first argument. And what we get are these four terms. The sum of these four terms is certainly less than or equal to when we take the absolute value of the second and the third term. Now let's look at the second and the third term more closely. In absolute value, these two terms are actually equal because they are complex conjugates of each other. So we may write this as 2 times the absolute value of the inner product of x1 with x2. And now we can apply the Cauchy-Schwarz inequality, which yields that this is less than or equal to 2 times the square root of the inner product of x1 with itself times the square root of the inner product of x2 with itself. Substituting this expression into here leads to the following inequality. The norm of x1 plus x2 squared is less than or equal to this expression, where we realize that this expression can be written as, in brackets, norm of x1 plus norm of x2 squared. The triangle inequality clearly follows by simply taking the square root on both sides of this inequality. Since we have just shown that an inner product always induces a norm on an inner product space, all properties and results of normed spaces also apply to inner product spaces. By this, we particularly refer to the concepts of convergence, Cauchy sequences, and completeness. Similar to normed spaces, we also have a name for inner product spaces that are complete, with respect to their induced norm, and such spaces are called Hilbert spaces. An important property of the norm and the inner product is that they are both continuous as functions. In definition 516, let's first recall the definition of a continuous function, which we have seen in a similar way in definition 4.3. The only specialty here is that we're looking at a particular class of functions, namely those which map from a normed vector space V into the field and which are also called functionals. In other words, the only special thing about a functional compared to a normal function is that a functional maps from a vector space into a field. Nonetheless, the usual definition of continuity of a function also applies to a functional. So the functional f is called continuous at some point x bar in the vector space if the following condition is satisfied. This condition is again a classical epsilon delta condition. So for every positive epsilon that's given to us, we must be able to provide a delta that may depend on epsilon, such that by keeping x inside a delta ball of x bar, we manage to keep the value of the functional f of x epsilon close to the value of the functional at x bar. If this is the condition for the functional to be continuous at some point x bar in the domain, then the functional is called continuous if it is continuous at all points x bar in its domain. Now let's first apply this definition to the case of a norm. This is proposition 517, where V is a normed space, then the norm, which is nothing but a map from the vector space into the real numbers, is continuous as a functional. Now, for the proof of proposition 517, for the norm to be continuous in general, so not at a particular point, we must show that it is continuous at every point x bar in its domain. So pick any arbitrary vector x bar in the vector space V, and in the following it will be shown that the norm is continuous at this vector x bar. To this end, suppose some positive value of epsilon is given. We now need to pick delta to satisfy this condition, and in this case we pick delta equal to epsilon. Now, the following two bounds can be obtained with the triangle inequality. First, we write the norm of the vector x like this, where we have subtracted x bar and added x bar, and we write the norm of the vector x bar like this, where we have subtracted x and added x. And now we associate these two vectors respectively, and we use the triangle inequality to get these results. In the first case, we bring this term to the other side and obtain this inequality. And in the second case, we bring this term to the other side and obtain this inequality. Now, by assumption, we have that the norm of x minus x bar is less than delta. So both of these terms on the right-hand side are less than delta. With delta equal to epsilon, as we have chosen it, it follows that the norm of x minus the norm of x bar is less than epsilon, and also the other way around, the norm of x bar minus x is less than epsilon, and hence the absolute value of the difference of the two norms must be less than epsilon. And we're done with our proof. Next, we have proposition 518, which states that we can pick an arbitrary vector x of an inner product space, and then we have that the inner products with x, so no matter whether we choose x to be the first argument of the inner product or the second argument of the inner product, are both continuous functionals. For the proof of proposition 518, part A, we assume that according to the statement, a vector x has been picked. And now to prove the continuity of this functional that maps from the second argument of the inner product, which is a vector, into the field, we fix again an arbitrary vector y bar in V and show that the functional is continuous at this point y bar. And since y bar is arbitrary, this implies that the functional is continuous in general. So let any positive value of epsilon be given to us. What must be shown is that there exists some delta of our choice such that whenever y is delta close to y bar, then also the difference between the inner product of x with y and x with y bar in absolute value is less than epsilon. In this case, we choose delta equal to epsilon divided by the norm of x, which works because x is a fixed vector. Then by linearity in the second argument, we can write this expression in this way. Then by using the Cauchy-Schwarz inequality, this is less than or equal to the inner product of x with itself to the power 1/2 times the inner product of y minus y bar with itself to the power 1/2. So this is exactly the induced norm of the vector x times the induced norm of the vector y minus y bar. And now by assumption, this norm here is less than delta, where delta has been chosen as epsilon divided by the norm of x. So the norm of x cancels here and we get exactly what we need, namely that this is less than epsilon. Part B of this proof is analogous to part A and therefore omitted, and therefore our proof is complete. Another thing that follows with an inner product is the notion of orthogonality of two vectors. And that notion is established in definition 519. So if we have an inner product space, any two vectors in that space, x and y, are called orthogonal if the inner product between x and y equals to 0. We will also have a shorthand notation for this by simply writing x is perpendicular to y. Now, a few remarks about this definition. First, it should be emphasized again that the notion of orthogonality requires the existence of an inner product. So orthogonality is not defined if we don't have an inner product, such as on general vector spaces or normed spaces without any inner product. Second, let S be a subset of vectors of a vector space. For example, S could be a subspace. Then if a particular vector x is perpendicular to all vectors in the set S, then this fact is expressed by writing x perpendicular to the set S. So this is just a convenient way of writing something that would otherwise require a lengthy notation. Third, let xk be a finite or infinite set of vectors. So this k here is a finite or infinite index set. Then this set of vectors is called orthogonal if for any two elements of this set, xk and xi, where k not equal to I, we have that these two elements are perpendicular to each other. And finally, such a finite or infinite set of vectors xk is called orthonormal if it is orthogonal and in addition all of the vectors inside the set have length 1 in the induced norm by the inner product. On this slide, we will look at two very fundamental results, namely the Pythagoras theorem and the Parallelogram law, and show that they hold in a very general setting, namely on any abstract vector space. So let's start with Theorem 520, which is the Pythagoras theorem. So let V be any general inner product space. Then for any two vectors x and y, where x is orthogonal to y, we have the Pythagoras statement, namely the norm of x plus y squared equals to the norm of x squared plus the norm of y squared. Of course, this is a much more general result than what we know as Pythagoras law in R2 or R3. And that's because it holds on any inner product space and therefore also on sequence and function spaces and so on. Nonetheless, with our framework of abstract vector spaces, it turns out to be very easy to prove, as we shall see in a moment. Before we do so, however, it's always a good idea to make sure that we properly understand the statement, and also it's a good idea to illustrate the statement in the simple and concrete case of R2 or R3. This is something that you should always do on your own when you see a result like this, to just become more familiar with the statement. And here I will do it for you. So let's draw two vectors x and y which are orthogonal to each other, as shown here. And now the specific Pythagoras theorem for R2 states that the squared length of the hypotenuse equals to the squared length of x plus the squared length of y. So how does this follow from the general statement in Theorem 520? Well, first, we know that the hypotenuse can be expressed as the vector x minus the vector y, because if I add it to the vector y, I will obtain the vector x. Note that the norm of the vector x minus y squared can also be written as the norm of x plus minus y squared, which by the statement of our theorem equals to the norm of x squared plus the norm of minus y squared. And of course, the norm of minus y squared is equal to the norm of y squared. As mentioned before, when you do research and you go through a research paper, for instance, you should be able to come up with little illustrations and examples like this on your own when you're facing some abstract result. But now let's look at the proof of Theorem 520. The proof is a good example of why abstract theory can be so useful. Namely, a result that would otherwise be very hard to prove in R2 or R3 suddenly has a very simple and elegant proof in a much more general setting. By the definition of an induced norm in Corollary 515, we can write the norm of x plus y squared as the inner product of the vector x plus y with the vector x plus y. By conjugate linearity in the first argument and linearity in the second argument, we can rewrite this inner product as the sum of four inner products. And now we observe that this inner product and this inner product are both 0 because x and y are orthogonal. And this first inner product equals to the norm of x squared, and this inner product equals to the norm of y squared. So we're done with our proof. In a similar way, we can show Theorem 521, which is the Parallelogram law. So again, let V be an inner product space. Then for any vectors x and y, which now don't have to be orthogonal, we have that the norm of x plus y squared plus the norm of x minus y squared equals to 2 times the norm of x squared plus 2 times the norm of y squared. The proof is part of the next homework sheet. However, let's do a little illustration here. So suppose we choose the vectors x and y in R2 like this, then the vectors x minus y and x plus y are given by these vectors. And now the parallelogram law makes a statement about the length of all of these vectors. Next, we'll look at a geometric interpretation of inner products that will lead us to one of the cornerstones in linear algebra, namely the projection theorem. So let V be an inner product space. For a little thought experiment, fix any vector x in V and let B in V be a unit vector, so B is of length 1, and define the subspace S as the span of this unit vector B. And this is illustrated in R2 in the diagram down here. So we have picked any vector x and a vector B of length 1, and the subspace S is spanned by the vector B. Now, by just using scalar vector multiplication and the inner product, we're able to construct the vector S star, which is the best approximation of the vector x inside the subspace S. The term best approximation refers to the fact that the error between the vector x and our best approximation vector S star, so the length of this vector here, is minimized. So for any other vector in the subspace S, for instance this vector here, the error would be larger than the error caused by S star. And this S star can be constructed by the formula shown down here. So we take the inner product of x with b and multiply it with b, and this will give us the best approximation of x in the subspace S. In fact, S star is the solution to the projection problem. Minimize over all vectors S in S the length of the difference between the vector x and the vector S. So the difference inside the norm corresponds to the error vector, and we observe that for the best approximation S star, this error vector is perpendicular to the subspace S, which is a property that holds more generally, as we will show in the projection theorem. To get to the projection theorem, let's first generalize the projection problem. So let V be any inner product space, so not necessarily R2 that we had before, and let S be any subspace of V, so not necessarily one-dimensional as before. Now fix any vector x in V and consider the problem of finding the best approximation of x in the subspace S in terms of finding the vector in S that minimizes the length of the distance between x and S. Then this problem will be called the projection problem, and it will be abbreviated with PP in brackets. In the statement of the projection problem, we have been careful to use the infimum instead of the minimum, because we're not sure yet whether such a vector S in S actually exists that attains the infimum of this length. But if the infimum is actually attained by at least one vector, which at this point is not necessarily assumed to be unique, so we just assume that there exists at least one vector S star in S, then we may write the minimum instead of the infimum, and we may write that S star is an element of the argmin of the norm of the vector x minus s for all vectors S in the subspace S. Such a vector S star in this argmin set will be called optimal. Remember that even if such a vector exists, it's not necessarily unique. What it would mean for an optimal vector to be unique is that it's the only vector in the argument set, or in other words, the argument set consists of exactly one vector. Based on this definition of the projection problem, we now have the projection theorem 522, which is really one of the cornerstones of linear algebra. The projection theorem is structured into three separate statements, A, B, and C, which read as follows. In statement A, the assumption is that the subspace S is complete, so we could also say that S is a Hilbert space. And in this case, the statement is that there exists a vector S star in S that attains the infimum of PP. In other words, there exists at least one optimal vector. For statement B, it is assumed that the infimum of the projection problem is attained by at least one vector, so there exists some optimal vector in S. This holds in particular under the assumption that the subspace S is complete according to part A. Now, part B claims that if the infimum of the projection problem is attained by some optimal vector in S, then some vector S star in S is optimal if and only if the difference between X and S star is perpendicular to the subspace S. Moreover, the optimal vector S star is unique. Finally, the third statement C of the projection theorem is concerned with cases where S is finite dimensional and complete. So we have some basis that we call B1 through Bn. Then the unique solution to the projection problem, S star, is given as a linear combination of the basis vectors, where the scalars alpha k are determined by solving a linear equation system. So we stack up the scalars alpha 1 through alpha n in a vector, and they are determined by inverting a matrix and multiplying it with a vector that consists of inner products of the basis vectors with x, and the matrix itself is determined by some inner products of the basis vectors. Let's prove theorem 522, beginning with part A. The assumption is that the subspace S is complete, which, as we remember, means that every Cauchy sequence in S converges to an element of S. Let's define the number gamma as the infimum of the projection problem. What we must show is that there actually exists a vector S star in S that attains this infimum, meaning for which the norm of x minus S star is actually equal to gamma. From the definition of gamma as the infimum of the norm of x minus S, it is clear that the norm of x minus S must be greater than or equal to gamma for all elements S in the subspace S. Moreover, for every positive value of epsilon, it's possible to find a vector S in the subspace S such that the norm of x minus S equals to gamma plus epsilon, meaning that we can find vectors S which produce a norm x minus S that's arbitrarily close to gamma. Now define a sequence of epsilon n, with epsilon n being positive real numbers and the limit of epsilon n going to 0 as n goes to infinity. So for example, we can just take epsilon n equal to 1 over n. Based on the previous statement, there must hence exist a sequence of vectors Sn in the subspace S with the property that the norm of x minus Sn is less than gamma plus epsilon n for all n in the natural numbers. The following identity follows from the parallelogram law of Theorem 520, as you can quickly verify for yourself. You take the squared norm of the sum of two vectors plus the squared norm of the difference between these two vectors, and this equals to 2 times the squared norm of the first vector plus 2 times the squared norm of the second vector. Here, sk and si obviously represent two elements of the sequence of vectors Sn. In the first term, apparently the vector x cancels out, so it can be written as the squared norm of sk minus si. By bringing this term to the other side, we obtain this equation, where we now proceed to bound each of the 3 terms on the right-hand side separately. If we choose both indices k and I greater than n, then we can bound the terms as follows. First, the norm of sk minus x squared is obviously less than gamma plus epsilon k squared, which in turn is less than gamma plus epsilon n squared. And the same thing holds for the squared norm of si minus x. It's less than gamma plus epsilon I squared, which is less than gamma plus epsilon n squared. The third term can be written as the squared norm of sk plus si minus 2x. And by pulling out a factor of -2, the vector inside the norm becomes -2 times x minus the sum of sk plus si half. And now we pull out the factor -2 in front of the squared norm to get that this is 4 times the norm of x minus sk plus si half. And since this expression clearly represents a vector in the subspace S, this means that the norm has to be greater than or equal to gamma, and hence the entire expression has to be greater than or equal to 4 gamma squared. Substituting these 3 bounds into the equation from the previous page, we get that the squared norm of sk minus si is less than 4 in brackets gamma plus epsilon n squared minus 4 gamma squared for all indices k and I greater than n. The expression on the right-hand side can be simplified a little further by multiplying out this quadratic term, and if we do that, we see that we can cancel out the term for gamma squared, and we get that the squared norm of sk minus si is less than 8 gamma epsilon n plus 4 epsilon n squared. So apparently we can make the squared norm of sk minus si arbitrarily small by choosing n large enough and hence epsilon n small enough. Hence, also the non-squared norm of sk minus si can be made arbitrarily small by choosing n large enough and the indices k and I greater than n, which is stating exactly that the sequence Sn is a Cauchy sequence. Because the subspace S is complete by assumption, the Cauchy sequence converges to some element S bar in S. And it remains to be shown that the vector S bar is optimal, so the norm of x minus S bar equals to gamma. And this follows from the observation that gamma is less than or equal to the norm of x minus S bar, because S bar is a vector in the subspace S, which can be written as the norm of x minus Sn minus S bar minus Sn in brackets, and then using the triangle inequality, this is less than or equal to the norm of x minus Sn plus the norm of S bar minus Sn. And now the first term goes to gamma, and the second term goes to 0 as n goes to infinity. Now we get to the proof of part B of the projection theorem. The assumption here is that there exists at least one optimal vector of the projection problem. And what we have to show is that a vector S star is optimal if and only if the difference x minus S star is perpendicular to the subspace, and moreover, this vector S star is unique. And we will prove this in 3 steps. For the first step, assume that S star in S is an optimal vector, and we write here an optimal vector instead of the optimal vector, because we have not shown uniqueness yet. We only know that an optimal vector of the projection problem exists. And we will first prove that x minus S star is perpendicular to the subspace S. So for the sake of a contradiction, suppose not. This means that there exists a vector S bar in S such that the inner product of S bar with x minus S star is non-zero. So here it's equal to some value alpha, which is not 0. Now define another scalar beta as the scalar alpha divided by the norm of S bar squared, where the norm of S bar is clearly non-zero because the vector S bar cannot be the 0 vector. And also define a new vector that we call S star star as S star plus the scalar beta times S bar, where clearly S star star is an element of the subspace S because S star and S bar are both in S. Now observe that the norm of x minus S star star squared can be written as follows. By the definition of the induced norm, the norm of a vector squared equals to the inner product of the vector with itself. And now we can apply conjugate linearity in the first argument and linearity in the second argument, as we've already done a couple of times. And what we get is the norm of x minus S star squared plus the norm of beta S bar squared minus this inner product minus this inner product. And now by linearity in the second argument, we can pull the scalar beta out of the first inner product, and by conjugate linearity in the first argument, we can pull out the scalar beta out of the second inner product. And next, we observe that this inner product is exactly the definition of alpha, and hence this inner product equals to alpha bar. So we get that the norm squared of x minus S star star equals to the norm squared of x minus S star plus the norm squared of beta S bar minus beta times alpha bar minus beta bar times alpha. Now we can pull out the scalar beta in the second term, and we can substitute for alpha the expression alpha equals to beta times the norm of S bar squared. What we get from this is the norm of x minus S star squared plus the absolute value of beta squared times the norm of S bar squared minus beta times beta bar times the norm of S bar squared minus beta bar times beta, the norm of S bar squared. But now we know that beta times beta bar and beta bar times beta equals to the absolute value of beta squared. So we end up with the squared norm of x minus S star star being equal to the squared norm of x minus S star minus the absolute value of beta squared times the squared norm of S bar. Substituting again our definition of beta, we get that this is equal to the squared norm of x minus S star minus the absolute value of alpha squared, which is clearly less than the squared norm of x minus S star, and hence we have a contradiction to the optimality of S star. Next, we prove the converse statement. So let S star be any vector that satisfies that x minus S star is perpendicular to the subspace S. We will now show that this implies that S star is optimal. Observe that for any vector S in the subspace S, it holds that the squared norm of x minus S can also be written like this, where we have inserted a minus S star plus S star. And this again can be written as the inner product of this vector with itself by the definition of the induced norm. And now we can again use linearity in the second argument and conjugate linearity in the first argument to write this in terms of 4 inner products, of which 2 become the squared norm of x minus S star and the squared norm of S minus S star. And the remaining 2 are the inner product of x minus S star with S star minus S and S star minus S with the vector x minus S star. Now notice that since S star and S are both elements of the subspace S, this vector and this vector are both vectors in S, and by assumption x minus S star is orthogonal to any vector in S, so therefore these 2 inner products here have to be equal to 0. Now looking at the remaining equation and noting that the squared norm of S minus S star is always non-negative for all S in S, it immediately follows that the squared norm of x minus S must be greater than or equal to the squared norm of x minus S star for all S in S, which is exactly saying that S star is optimal. Finally, for part B, it remains to be shown that the optimal vector is unique. So suppose S star and S bar are 2 optimal vectors. To prove uniqueness, we will show that S star has to be equal to S bar. To this end, consider the squared norm of S star minus S bar, which we can also write as the inner product of S star minus S bar with itself. And now in the first argument, we can subtract and add the vector x. So by conjugate linearity in the first argument, this equals to the inner product of S star minus x with S star minus S bar plus the inner product of x minus S bar with S star minus S bar. By assumption, S star and S bar are both optimal, and hence, by what we have proved before, this means that x minus S bar inner product with any vector in S, and also inner product of S star minus x with any vector in S must be equal to 0. So we get that the squared norm of S star minus S bar equals to 0, which of course implies that S star equals to S bar. Finally, the proof of part C of the projection theorem is omitted at this point because it requires some results that we will only introduce in the next chapter. So this completes the proof of the projection theorem. Next, we look at a fundamental algorithm called the Gram-Schmidt procedure. So consider a collection of vectors C1 through Cn in an inner product space V. The Gram-Schmidt procedure can be used to construct a set of vectors B1 through Bm that forms an orthonormal basis for the span of the vectors in the set C. Note that the number of basis vectors m is not necessarily the same as the number of original vectors n, and that's because some of the vectors in the set C could be linearly dependent, and in this case m would be strictly less than n. If all of the vectors in C, however, are linearly independent, then m and n will be equal, And all that we're getting out of the Gram-Schmidt procedure is an orthonormalization of the vectors in the set C. The way the Gram-Schmidt procedure works is described in algorithm 523. It starts with the first vector C1 in the set C, and then it moves through the entire set C stepwise by gradually increasing the index k, where the next vector bk is computed based on the vector ck and some inner products with the already computed basis vectors bj up to the current instance k. You will actually go through an example of the Gram-Schmidt procedure on the next homework sheet 5. On the last slide in this chapter, we will get to the important concept of an orthogonal complement. What we mean by an orthogonal complement is stated in definition 524. So let S be any subspace of a Hilbert space. Then the orthogonal complement of S is the set of all vectors x in V which are orthogonal to the subspace S. And we denote the orthogonal complement as S with this little orthogonal sign in the superscript. As a little forward reference, the orthogonal complement will play a major role when later on we talk about the controllable and unobservable subspace of a linear system. For now, we just state a few basic facts about orthogonal complements in lemma 525. So let V be a Hilbert space with a subspace S, then the following statements hold for its orthogonal complement as perp. A as perp is also a subspace of V. B as perp is complete. C as perp is a superset of S. D, if S is complete, then V can be written as the direct sum decomposition of S and S perp. And E, if S is complete, then S perp equals to the subspace S. So let's prove the statements in lemma 525. For part A, according to Theorem 415, S perp is a subspace if and only if it is closed under scalar multiplication and vector addition. So pick any two vectors x1 and x2 in S perp, which means that the inner product of x1 with S and the inner product of x2 with S equals to 0 for all vectors S in the subspace S. Now note that for any scalar alpha, we have that the inner product of alpha x1 with S equals to alpha bar times the inner product of x1 with S, which is 0 by assumption. So therefore this is 0, and hence alpha x1 is an element of S perp. Moreover, the inner product of x1 plus x2 with S equals to the sum of the inner products of x1 with S and x2 with S, which are both 0, and hence also the vector x1 plus x2 is an element of S perp. For statement B, where we want to show that S perp is complete, we consider, of course, a Cauchy sequence in S perp. However, since S perp is a subspace of V, this implies that the sequence xk is also a Cauchy sequence in V, and by assumption, V is a Hilbert space, so it's complete, and therefore this Cauchy sequence in V has a limit in V, which we call x bar. Clearly, we have to show that x bar is an element of S perp. To this end, pick any element S in S and consider the inner product of x bar with S. For x bar, we can also write the limit of the sequence xk as k goes to infinity. And now by proposition 518b, we have that the inner product is a continuous function in the first argument, and therefore we can take the limit out of the first argument and have that this is equal to the limit as k goes to infinity of the inner product of xk with s. And since all the xk are in S perp, these inner products are all 0, and we have that the limit as k goes to infinity of the 0 sequence is of course equal to 0. With the inner product of x bar with any vector s in the subspace S being 0, this means exactly that x bar is an element of S perp, and we have finished the proof of part B. The proof of part C will be part of exercise sheet 5. For part D, the statement was that if S is complete, then V can be written as the direct sum decomposition of S and S perp. So for the proof, fix any vector x in V. According to definition 4.17 of the direct sum decomposition, what we need to show is that x can be uniquely written as the sum of two vectors s and s bar, where s is an element of the subspace S and s bar is an element of the subspace S perp. According to part A of the projection theorem, because S is complete, there exists an optimal approximation vector of x inside the subspace S, which we define here as the vector little s in the subspace S. Note that we can express x in this way, where we have added and subtracted this optimal approximation vector s in S. Now clearly S is an element of the subspace S, and x minus s turns out to be an element of S perp. That holds because S in S is the optimal approximation of x in the subspace S. So by the projection theorem part B, x minus s is perpendicular to the subspace S, and hence x minus s is an element of S perp. So we have shown that any vector x in V can be expressed as the sum of one vector in the subspace S and one vector in the subspace S perp. What remains to be shown is that this decomposition is in fact unique. To prove uniqueness, suppose we can write the vector x as the sum of S and S bar, as well as Q and Q bar, where S and Q are in the subspace S, and S bar and Q bar are in the subspace S perp. Bringing Q to the left side and S bar to the right side, we get that S minus Q equals to Q bar minus S bar, where now the vector on the left-hand side is clearly an element of the subspace S, and the vector on the right-hand side is clearly an element of the subspace S perp. So the two vectors S minus Q and Q bar minus S bar are orthogonal to each other, which means that their inner product is equal to 0. This implies, on the one hand, that the inner product of S minus Q with S minus Q, which is equal to the squared norm of S minus Q, is equal to 0. And that's because for Q bar minus S bar, I can substitute S minus Q. And on the other hand, it means that the inner product of Q bar minus S bar with Q bar minus S bar, which equals to the squared norm of Q bar minus S bar, is also 0, because I can substitute for S minus Q, Q bar minus S. Because the norm of a vector is 0 if and only if the vector itself is 0, the first equation implies that S equals to Q, and the second equation implies that Q bar equals to S bar, and hence we can deduce that these two decompositions are one and the same. And we have finished the proof of uniqueness. Now for part E of Lemma 525, this will again be a homework problem on exercise sheet 5, and hence we're done with the proof of Lemma 5.25.